Hello, Physics 20s. In today's lesson, I'm going to talk in more detail about the force of friction. And more specifically, if we look at the learning outcome from the Physics 20 program of studies, we are going to explain, both qualitatively and quantitatively, static and kinetic forces of friction acting on an object. Start off with a really simple scenario where I have an object, we'll say it's just a box, and this box is in direct contact with some type of surface. That surface could be the ground, a lab counter, the top of your desk. If I were to ask you right now, what factors would result in the force of friction acting on an object to be larger, what would you say? Usually when I ask this question, students give me three answers. And the answers to this are: one, the force of friction depends on the weight of the object. The rationale: objects with larger weights are more difficult to move. They're more difficult to move because the force of friction must be larger. The second answer is typically something to do with the surface itself, like how rough or smooth the surface is. For example, if you dragged like this box along some concrete compared to like the top of the desk, the surface that's rougher, which would be the concrete, you'd expect the force of friction to be a little bit bigger. So we'll write down the surface in contact. The third one I usually get as a response is, what is the surface area that the box is in contact with the ground? For example, you could have the box so that one side of the box, there's a lot of the box that's in contact with the ground, compared to if we tip the box up here, then we have a smaller surface area in contact with the ground. So in the case on the left-hand side, there's more of the area in contact with the ground, and on the right-hand side, there is going to be less surface area in contact with the ground. And usually the rationale here is the more of the object that's in contact with the ground, there's more particles that make up that object. Each of those particles would be subjected to a force of friction, resulting in a larger overall force of friction on the object. Of those three factors that I've just identified here, I'd say 1.5 of them are correct. So let's go through all the different factors the force of friction depends on, and we'll come back to like the three predictions that, again, like most people usually tell me when trying to identify what factors the force of friction depends on. The magnitude of the force of friction depends directly, and we'll look at a mathematical equation in a moment, directly on the magnitude of the normal force acting on the object from the surface. I said 1.5 of those three were correct because the normal force is dependent on the weight. If you drew a free body diagram of that box on the ground, you'd have the force of gravity straight down. So that's Fg. You'd have the normal force that's straight up, Fn. In this case, the normal force would just be equal to the force of gravity. Therefore, if you have an object with a larger weight or force of gravity, its normal force is going to be bigger. The bigger the normal force, the bigger the force of friction. So just to give you a bit more specific, instead of saying it depends directly on the weight, it actually depends directly on the normal force, where the normal force depends on the weight of the object. That's my first one. 2, the force of friction is dependent, I'm just going to erase this. The force of friction is dependent on the nature of the materials that make up the object and the surface. So not only does it depend on like what surface you're pulling the object on, it also depends on the smoothness or roughness of the object that you're pulling. When I say the nature of the materials, it just means what is the ground made up of and what is the actual object made up of. Depending on what materials make up the object and the surface, that is going to have an effect on the force of friction. And typically, the rougher the surface is in contact, the larger the force of friction is going to be. The force of friction only depends on these two factors. So the one that we are not seeing here is there's no dependency on surface area. So in a way, it depends on weight, depends on the normal force. It depends on the surfaces in contact, but it does not depend on the surface area. Here's a little bit of a rationale for this. Let's look at our two scenarios. One where I have this box where it has like a large amount of surface area in contact with the ground, and then we can take the box and put it on its side. So it has less surface area in contact with the ground. I'm going to break the box up into, let's say like a few segments right here. We'll just say like, here's one little segment. Here's another little segment. Another one. Another one. Another one. So this one right here has 5 segments to it. This one right here, we'll just break it up into two segments. Each of these segments would be subjected to a normal force. I mean, technically, like, it's not 5 segments. You could break it down into like billions and billions of segments if you wanted to, but each one of these segments would be exerting the force of gravity on the ground. So the ground's going to exert an equal and opposite normal force back on the box, and on every part of the box. So each of these 5 segments here is going to have a normal force that reacts to the force of gravity of the box and just points straight up. The difference right here is when the box is on its side, the magnitude of the normal force is actually going to be larger on these 2 segments. So this one right here only has a normal force acting on segments 1 and 2. This one has a normal force acting on segments 1, 2, 3, 4, and 5. In scenario 1 on the left-hand side, each segment would experience a smaller normal force. And in the scenario on the right-hand side, each segment would experience a larger normal force. If you add all of these vectors together and just represented the normal force with a single vector, maybe like Fn, if you add 5 small normal force vectors together, you get this one. And on the right-hand side, if you add these 2 larger normal force vectors together, you would also get the same magnitude of the normal force. So either way, regardless of like what area is in contact with the ground, the object is still subjected to the same normal force. If I'm subjected to the same normal force, then it's going to be the same force of friction magnitude that, the same force of friction magnitude as a result of that normal force being the same on the box. So the surface area actually does not matter. Let's just quickly erase this picture before I show you an equation. Sorry about that. I probably could have just cleared everything off the screen, but oh well. To calculate the magnitude of the force of friction, we can use the following equation. The magnitude of the force of friction is equal to, you got some funky symbol that looks like a handwritten U. That handwritten U is a letter of the Greek alphabet. I think it is a lowercase letter called mu. I don't know if I'm spelling mu correctly, but it's part of the Greek alphabet. Magnitude of the force of friction is equal to mu multiplied by the magnitude of the normal force. Whenever I have magnitude of a force vector, I find it easier just to write the force vector or just the force like this. So just write down FF without a vector sign. F without a vector sign would just mean the magnitude of that force. That's going to be equal to mu times Fn. Excuse me. Going back to what the force of friction directly depends on, so there's a direct relationship between the force of friction and the normal force, and it also depends directly on the surfaces that are in contact. This coefficient, mu, is going to have something to do with the surfaces that are in contact. We'll get into that a little bit later. Mu, we call it the coefficient of friction, and it's a coefficient of friction between a specific object and a specific surface. So it has everything to do with the nature of the materials that make up both the object and the surface. And again, we'll come back to this a little bit later in the lesson. If you look at the equation, there are actually no units for the coefficient of friction. We know this because, well, the force of friction would be measured in units of newtons. The normal force is also measured in units of newtons. So if I take the normal force and multiply by the coefficient of friction, it needs to be unitless to get the newtons for the force of friction. It turns out that there's actually two different ways we can categorize friction. There's one category called static friction and one called kinetic friction, and that's what we'll go through over the next two slides, and we'll distinguish between these two types. Static friction is the force of friction that prevents an object from moving in the first place. So, for example, if you had like the ground, you have like a really, really heavy object, and you try to take this object and pull it towards the right with an applied force, the force of friction would prevent you from moving. Because you don't move, we call that static friction. Think back to how we classified static and dynamic equilibrium. Static equilibrium was dealing with scenarios where objects were not moving. So same thing right here. Static friction deals with friction that prevents an object from moving in the first place. And it would always be in a direction that is opposite to the attempted direction of motion. In this case, you're trying to move the object towards the right, and the force of friction would just oppose towards the left. The magnitude of the static force of friction is not a constant. In fact, what it'll do is it's going to change depending on how hard you actually pull on the object. If you pull on the object with a small force, then the static force of friction opposes with a small force. If you exert a force on the object, a much larger force, and you still can't get it to move, the static force of friction would be much larger in magnitude. Now, let's look at this in more detail. Let's say that we exert an applied force on an object, and we start to increase that applied force. What will happen is, as you increase that applied force, the static force of friction is essentially just going to match your applied force. Match in a way that is going to result in the forces on your object balanced and the object not moving. Let's look at a more specific example. Let's say that we have an object and we're going to apply a force towards the right, in which case force towards the right we could identify as being positive towards the right. If I exert a force on the object towards the right, an applied force, and I can't get it to move, that's because the force of friction is equal in magnitude but opposite in direction. If you look at the sum of the forces in the x direction, it would just be Fa plus Ff, which would be positive 100 newtons plus negative 100 newtons. The net force would be 0. If the net force is 0, then the object doesn't move. So static friction is the force of friction in this situation that is preventing me from moving in the first place. If you increase the magnitude of this force to positive 200 newtons, Well, once again, the force of static friction is just going to offset your applied force. If the object's not moving in static equilibrium, it means the sum of the forces is equal to 0. Therefore, if you increase the applied force to positive 200 newtons, the force of friction would then increase to 200 newtons of force, although in the opposite direction. This is what I mean by the magnitude is not constant. The magnitude of the applied force is just of the force of friction is going to change depending on how hard you pull on the object. Eventually, as you start to increase that applied force, you're eventually going to reach a point where you can get the object to actually move. If you do pull hard enough, I could get that box to accelerate towards the right. So there is a limit in terms of how big the static force of friction can be. We'll call that point where I can just get the object to move the breakaway point. And when I get to that breakaway point, let's call it the breakaway point here. The breakaway point would be when your applied force is finally bigger than the force of static friction. If it's bigger than the force of static friction, then you have an unbalanced force that would be towards the right in this situation. And then that caused me to accelerate towards the right according to Newton's second law of motion. Just before that breakaway point, that is where my static force of friction is a maximum. Just one instant prior to whatever that breakaway point is. For example, maybe the breakaway point is when the applied force is 300 newtons. Therefore, your static force, your maximum static force of friction would be the last point where the static force of friction could offset the applied force. We can calculate the maximum static force of friction using the following equation. Now, this only gives us the actual maximum static force of friction. Your maximum static force of friction, the magnitude, is equal to mu s. Mu, again, is something called the coefficient of friction, which we'll get into in a little bit later. I've added a subscript right there just to identify that I'm dealing with static friction. In fact, if I wrote this equation out, I'd make it a bit simpler. I would just write down the force of friction, FF, is mu s times Fn. That's the magnitude of the static force of friction, although this equation is only useful at the maximum point. We'll call that maximum point the instant before the breakaway point. Otherwise, in the case we shown right here, the force of friction would just be equal and opposite to whatever the applied force is. Although I could calculate the maximum static force of friction acting on an object if I just knew what the coefficient of friction was and if I knew what the normal force acting on the object was. I wouldn't have to actually go through the trial and error of gradually increasing the applied force until I get to the breakaway point. I could just simply use the equation to calculate the static force of friction at that max point. So that's static friction, friction that prevents an object from moving in the first place. Our second type of friction is kinetic friction. Kinetic friction is friction that acts on objects that are in motion. So once again, we could go to a situation where I have a box that's like on a surface. And in this situation, let's say that the sum of the forces is not equal to 0. And I could represent this if I showed the applied force towards the right and the force of friction a little bit smaller in magnitude. if I look at the tug of war winner between the applied force and the force of friction, the applied force and the force of friction, the applied force wins. It's larger in magnitude than the force of friction. So my object is going to move. In this case right here, the velocity of the object would be towards the right. The direction of the force of friction is always opposite to the direction of motion. I just want to be a bit more specific about what I mean by motion right here. Motion for kinetic friction would be opposite to the direction of a velocity vector. The reason I want to point this out is because I just want to show how velocity and acceleration could be related to the direction of the force of friction. In the picture I showed on the top of the screen, if the applied force is bigger than the force of friction, you'd have a net force that's towards the right, which means that your acceleration is also towards the right. So both the force of friction would be opposite to both the direction of the velocity of the object and the direction of the acceleration of the object. I could have a scenario where maybe I have like a sheet of ice and I have a little box and I just give it a little push. Just a little push, then I let go. Little push, and then I stop. A little push, and I let go. I don't exert a force on the object anymore. What would happen is after you push the object on the ice, it would move towards the right, so its velocity would be towards the right. Now, the object, after you push it, would slow down. If you have a situation where your object is slowing down, your velocity and acceleration vectors must be opposite in direction. In this situation, so after you take an object and it's on the ice and you give that little initial push and then let go, its velocity is towards the right, it's slowing down, which means its acceleration is in an opposite direction. The acceleration is towards the left because it's going to make this velocity towards the right decrease. In this situation, the force of friction would also be pointing towards the left. I just wanted to point this out because it is possible to have scenarios where both your acceleration and force of friction are in the same direction. Going back to this bullet point right here, whenever you draw the force of friction vector, it should always be opposite in direction to your object's velocity, not necessarily the acceleration. Unlike the static force of friction, the magnitude of the kinetic force of friction is essentially constant. What that means is it doesn't matter, once an object's in motion and there's friction acting on it, it doesn't matter how hard you pull on the object. For example, let's say that we're pulling an object towards the right with a 100 Newton force. And then let's say that your force of friction value is 20 Newtons. If I increase this one to 200 Newtons, the force of friction still stays as 20 Newtons. So it doesn't matter what applied force you exert on the object, your magnitude is for the most part constant. And we can look at a graph to show what this looks like in a moment. In terms of calculating the kinetic force of friction magnitude, it would just be equal to the coefficient of, this is called kinetic friction. So the K right here tells me I'm dealing with kinetic friction, multiplied by the normal force. I'd write this a little bit differently, dropping the absolute value vector symbols and just write down the force of kinetic friction, FF, is equal to mu K times Fn. When I'm solving problems and I want to distinguish between kinetic and static friction, the only way I do that is that I show it with the subscript attached to the coefficient of friction value. I don't write it in the FF term. Usually just beside the mu value, I'll identify if it's mu K or it is mu S. This graph is a graph of the magnitude of the force of friction acting on an object over a certain amount of time. I just wanted to use the graph just to show how the static friction changes and how the kinetic friction is roughly constant. So if we follow this, this could be just us pulling on a box. In this part of the graph right here, what we have is the static friction it's not the same. It keeps changing. The reason it keeps changing is because in this part of the graph right here, your static force of friction is going to match whatever the applied force is. So presumably what's happening in this scenario is a person is just pulling on the object harder and harder. And as they pull harder and harder, the force of friction just matches that equal and opposite force. At the very top here, so this is your maximum static friction point, right before the breakaway point, we can calculate the force of friction at that point. The force of friction at that point would just be equal to μs times Fn. So again, this equation is only valid for static friction at your max point. After this, you can see right here, it looks like the force of friction drops to something smaller. I don't know if you've ever experienced this, but sometimes it seems like if you have an object at rest and you're trying really, really hard to get it to move, that like you have to exert like more and more force, and you're like, you really just want the object to like start moving. You're like exerting force. You're like, oh my goodness, I don't know if I'm ever going to be able to get this thing to move. And then once you get it to move, suddenly it's like it's easier to push, or it's easier to get the object to move. It's almost like the friction relents after you do get past that static friction breakaway point. And that's what I see right here. The kinetic friction is suddenly smaller in magnitude. I said it's roughly constant. I mean, if you look, it has like some like bumps and dips in the road. If I drew a line of best fit through it though, like it would roughly be just a horizontal line. So no matter like what applied force I'm exerting on the object, once the object's moving, your force of kinetic friction would just be the coefficient of kinetic friction multiplied by the normal force. So it's kind of like three different parts to like friction. There's the part where the object's not moving and you're applying a larger and larger force trying to get it to move, in which case the force of friction is just offsetting the applied force. You have two, that max point, where if you wanted to, you calculate the maximum static friction value, μs times Fn, and you'd have like the third part of the motion, which would be once you get the object to move, then no matter what force you're applying, the kinetic force of friction is just μk times Fn. Let's talk about that coefficient of friction in a little bit of detail. I've already mentioned that the coefficient of friction is dependent on the nature of the materials that are in contact. So not just the material of the surface of whatever you're moving the object on. It would depend on what your object's made up of and also what the surface is made up of. And the rule is the smoother the surface, the smaller the coefficient of friction value would be. The rougher the surface is in contact, the larger the coefficient of friction value would be. Larger coefficient of friction value would give you a larger force of friction. I did say determined experimentally. There is a lab performed in Physics 20 where we can experimentally determine the coefficient of friction between two different surfaces. So it is possible to determine it, but it does require like an actual experimental setup to figure out what the coefficient of friction value is between different surfaces. But we're not going to worry about that right now. Right now, we'll just be given the coefficient of friction values to play around with in our calculations. In general, when you compare the coefficient of static friction to the coefficient of kinetic friction, your coefficient of kinetic friction is going to be smaller than the coefficient of static friction. This makes sense if we go back to the previous graph. let's say in this situation that the normal force acting on the object was 20 newtons. If we go to this equation right here and we had 20 newtons from a normal force, and go to this equation for 20 newtons for the normal force, let's just pick a different color here. In order to get, if in both situations you have the same magnitude of the normal force, then in order to get a larger static force of friction value, this means that the mu(s) would have to be a bigger number. For the kinetic force of friction, since the kinetic force of friction is lower in magnitude, with a constant normal force, you would need to have a lower coefficient of kinetic friction to get that smaller kinetic friction value. Here's an example of a couple of surfaces. Maybe we'll just look at the just the first one just to show the difference. So this could be like you have a wooden box and you're pulling it along like a piece of plywood. So wood being pulled along wood. In that scenario, my coefficient of static friction is bigger than the coefficient of kinetic friction. If you take that wood and you pulled it on snow, well, these surfaces would be in comparison to wood on wood. So wood on wood would be rougher surfaces. Waxwood on snow would be smoother. The smoother the surface is in contact, the lower both the coefficient of static friction and the coefficient of kinetic friction would be. Let's look at an example problem now. I have a 10 kilogram box that's being dragged from rest across a level floor with a force of 60 newtons and an angle of 30 degrees above the horizontal. I'm given the coefficient of kinetic friction value between the box and the floor, and I want to calculate three things: magnitude of the normal force acting on the box, magnitude of the acceleration of the box, and I want to know what the final velocity of the box is after I pulled it for 5 meters. This is a dynamics problem because we're dealing with forces. So we start off with the same procedure we've been using the entire unit, which is to draw a free body diagram. So we'll do an FBD. Draw my box. I have the force of gravity acting on the box, which should be straight down. Oops. Force of gravity, not the normal force. FG. I have a normal force that would point up. Call it Fn. I have an applied force that's up at an angle. Fa. The assumption I'm making in this problem is this mass is heavy enough that even if I apply a force up at an angle, the box is still being dragged horizontally along the ground. So my velocity would be towards the right, which means the force of friction would then be towards the left. And we'll call that FF. I'm not supposed to draw the components of an angled vector on a free body diagram, but again, we'll compromise just by using dashed lines. The vertical component we'll call FAX. The horizontal component we'll call FAY. And this angle is theta. That's my free body diagram. mass acceleration diagram. M. And again, we're dragging the object horizontally along the ground, so my acceleration would just point towards the right. Part A wants us to figure out what is the magnitude of the normal force acting on the box. This is the part where we would go to deriving equations of motion to mathematically model a situation. In terms of what equation of motion you would start with, well, look, the normal force is in the y direction. Therefore, I would want to start with the y direction equation of motion to get the normal force. We'll say up is positive, and I want to find the sum of the forces acting on the object in the y direction. Now, if you look at the mass acceleration diagram, there is no acceleration vertically. In fact, there is no motion vertically. The mass is just being dragged horizontally along the ground. If there is no motion or no acceleration vertically, then that means the sum of the forces in the y direction is 0, which means these forces are balanced. Let's expand the sigma f part. So again, this means look at the free body diagram, look at the forces in the y direction. If it points up, put a plus sign in front of it. If it points down, put a minus sign in front of it. If you look at the free body diagram, there are 3 forces in the y direction. There is this normal force pointing up, the applied force vertical component that points up, and the force of gravity that points down. So 3 of them. Therefore, I would have Fn, which is positive, plus Fay minus Fg is equal to 0. Let's expand this a little bit. I'm going to bring this up here. So I would have Fn plus Fay could be broken down into Fa sine theta. Fg is just m times g. If we can get the normal force by itself by adding mg to both sides and subtracting Fa sine theta. Therefore, I'd have Fn is mg minus Fa sine theta. And now it's just a matter of plugging the numbers in to calculate the normal force magnitude. So we'll do that. The mass is 10 kilograms. G is the magnitude of the acceleration due to gravity. We do not need to put a negative sign in front of it. We already dealt with the negative over here, where we have the negative in front of the Fg. Subtract, the applied force is 60 newtons. Multiply by sine of 30 degrees. And then that would give me the magnitude of the normal force would be equal to, and the number I've got is 68 newtons to 2 significant digits. That's part A. Part B wants me to calculate the magnitude of the acceleration of the box. Well, the acceleration's in the x direction, so we're going to use our equation of motion in the x direction to do this. Before I go to the next slide, let's just quickly look at the free body diagram and look at the forces in the x direction. We have 2 of them. We have the horizontal component of the applied force, Fax. It points right. It's going to be a positive. And we have the force of friction, which points towards the left. It's going to be negative. Let's clarify what direction we want to be positive. So we'll say right is positive. And I want to find the sum of the forces acting on the object in the x direction. And that's mass times acceleration in the x direction. Because you have acceleration, it tells me that the forces are unbalanced. Unlike in part A, the forces in the y direction were balanced because you had no acceleration in that direction. Let's expand the equation of motion. So Fax points towards the right, therefore it's positive. The force of friction points towards the left, it's negative. That would be equal to m times A is towards the right, therefore it's positive. We can expand both terms on the left-hand side. Fax just becomes Fa cos theta. The force of friction, well, we have an equation for that. If we're talking about kinetic friction, the force of kinetic friction is just equal to the coefficient of kinetic friction multiplied by the normal force. So we can plug that in. So that would then be mu k Fn is equal to mass times acceleration. I want to solve acceleration, so divide both sides of the equation by the m. So that I have A is equal to Fa cos theta minus mu k Fn. Divide this all by the mass. Let's plug the numbers in now. Fa was 60 newtons times cosine of 30 degrees. Subtract the coefficient of kinetic friction is 0.20. Your coefficient of friction values should always be a number that's between 0 and between 1. Closer it is to 0, the smoother the surface is in contact. Closer it is to 1, the rougher the surface is in contact. Normal force, we're just going to use the rounded value from part A. So I think we calculated it to be 68 newtons. Divide this by the mass. The mass is 10 kilogram box. Let's put the top of this calculation in its own set of brackets. We don't mess the order of operations up in our calculator. And then I would get A would be equal to, this is just the magnitude of the acceleration, 3.8 meters per second squared. And this is part B. Part C wants me to figure out what the velocity of the box is after being pulled for 5.0 meters. To do this, we need to draw upon knowledge from a previous unit because none of our dynamics equations so far deal with velocity. They only deal with forces and acceleration. To solve this, we want to set up a one-dimensional kinematics problem. So we're going to say that we have right is positive. And what I want to calculate is the final velocity of the box. So that's Vf. We're going to assume that the motion is uniformly accelerated motion, which means we can use those equations that have Vf, Vi, d, a, and t in it. In order to solve for Vf in one of those equations, you need to know 3 variables to get this one. So let's see what we actually know. Well, let's assume that we're pulling the box from rest. So we'll say Vi is equal to 0 from rest. We have the acceleration from part B, just right here. The acceleration is towards the right, so you'd put a plus sign in front of it. So we got 3.8 meters per second squared. And I also know, well, it tells me what's the final velocity after pulling it for 5.0 meters. That would be the displacement of 5 meters towards the right. The equation I'm going to use to calculate this is Vf squared is equal to Vi squared plus 2 AD. Vi is 0. Let's get rid of that term right away. Don't have to worry about it. And then that would just tell me that my final velocity, take the square root of both sides, would just be equal to the square root of 2 times A times D. Plug the numbers in. This would be 2 times A, which is positive 3.8, meters per second squared, multiplied by d, which is positive 5.0 meters. We want to take the square root of that number, and then that will give me a final velocity that is equal to positive 6.2 meters per second. And what that positive means in this situation is the final velocity is towards the right. Okay, so we talked about the force of friction. We talked about how we can break it into kinetic and static friction, and then we solved the problem where we used our approach of drawing free body diagrams and writing equations of motion, and we threw in an equation for the force of friction. So now we can solve some more complicated dynamics problems now knowing that we can deal with the coefficient of friction. And that is the name of the assignment that you need to complete, coefficient of friction, and I'll talk to you next time.